right. Well, good morning, everybody. Thank you very much for the opportunity to present to you this morning. As Tom mentioned, I'm Yaneev Golombek. I am a project manager at Woolpert and Company, and I'm here to talk to you about just some innovative approaches to mapping streetscapes and streetscape features. Specifically with mobile lidar, basically, before I start really getting into the gist of the mobile lidar collection, I'm just going to take ourselves on, I guess, a little bit of a journey here as to how we got to exactly where we are with this. And basically, it's the research, the study, it examines the use of lidar technology to measure urban streetscapes and urban features. And the study ties various quality levels of lidar tied to 3D volumetric pixels known as voxels. I will get into that in a little bit, to objectively measure how urban features are represented within a streetscape. Traditionally, when we're looking at features within a streetscape, we're just kind of looking more at a 2D view. And this just kind of goes more into a 3D view, and I'll get into the justification of why this work is actually important and what really was the drive from it, from the both transportation engineering and the urban design community. But basically, we're looking to devise new and objective methods to measure as many objects as possible within an urban streetscape. Street space, or streetscape as it's called. Some of you might be hearing the term streetscape for the first time here, but basically any kind of an urban environment really will have a street going through it, whether it's a pedestrian walkway or a vehicle roadway, some kind of an arterial street. But basically, the urban environment really composes the epicenter of that is the actual street space and everything that is around it. And there's been a drive within the within the research communities, specifically the transportation and the urban design research communities, to find more ways to objectively measure basically everything that's in the periphery of a street view, and to do so in in 3D. So what is the actual justification for this type of work? And it's basically, the concept of livable streets, like what makes a street more desirable. Urban planners are always trying to tackle this idea, and municipalities as well, that are trying to grow and bring people to their urban environments. They're often they're conflicted, but they're often looking just for ways to just kind of really understand what are the things within an urban environment that really make them more desirable, more livable, more walkable. So the study really intends to compose objective spatial measuring tools to contribute to research within these highly researched topics in transportation and urban design. So moving on, there's so again, continuing on really the justification for this work. So there's two parts of it. The part that I just mentioned really is what makes a street space more desirable. That is really broken into perceptual quality studies, and there's various perceptual qualities that people will look at to specifically see what they can do to enhance an urban streetscape, and also the concept of in an urban street space, transportation outcomes. That data has been very conflicted, and it's been conflicted for decades actually. So I'll start off with the topic of its relation to transportation safety. Right now we have a lot of conflicted research out there of the role that trees, and that kind of picks up from the previous keynote discussion that we're coming off of, and just landscape improvements and roadside features play in transportation safety. Traditional research really suggests that fewer trees and streetscape objects lead to safer driving environments. And specifically, if I look at this screen, the ASHTO, which is really the manual of how street spaces are really designed from this perspective of transportation safety through the Department of Transportation. There was this idea that and it's really the traditional concept of the bigger, how far off a roadway does a tree have to be? The bigger it is, the wider it is, the more the idea was it was more dangerous, and you would, if they had to be trees had to be designed a certain way, and depending on their size, basically offset from the street a certain distance, and that was really for safety. However, a bunch of transportation and urban design researchers in the academic communities, and I've listed a few here, they've come up with research in the past couple of decades that really suggests a little differently. They pretty much suggest that that the more trees you have, the overall number of crashes are reduced. There might be just a few more fatal crashes, and that might be related to things involving alcohol or just things that will generally be on the control of the designers. But research has really been conflicting, because there's a lot out there that's now saying specifically that that the more trees that you have on a roadway, it's actually safer, and that's likely because the perception of the drivers is heightened when driving in these environments. The problem is the studies really fall short of what specific elements lead to potential safer streets, because limited tools and methods to properly measure features within the streetscape, so those really don't exist. And that's really where the promotion of GIS technology and its tools, particularly Lidar, will really come into play, and that's really what I'm here to talk about. And they really do not evaluate really any sophisticated geospatial method to augment the analysis that a lot of researchers are doing. And a lot of these studies, if you go into the if you look into the academic platforms and whatnot, the studies are small. They're limited to a few blocks or a few limited linear miles, and and the question is that when we start using these sophisticated GIS and remote sensing measuring tools, as mentioned, Lidar, will the results hold? Will we find out something new about really what makes a street more safe to drive on based on the objects that are in the periphery of the drivers that are on them? So that's one part of it, is the idea of transportation safety. The other part I touched on a little earlier is this concept of perceptual qualities. And if you look at that box 1.1, specifically from Ewing and Clemente's publication, you'll see that this has been a topic that has been written about for over a century, really. Addressing perceptual qualities. Well, what are perceptual qualities? As I mentioned earlier, there are these things that make a streetscape really more desirable. Enclosure. Enclosure is the degree to which streets and public spaces are visually defined by buildings, walls, trees, and other vertical elements. Transparency, degree to which people can see or perceive what lies beyond the edge of a sidewalk. Human scale, the size and texture of physical elements and how they correspond to human size and proportions. Complexity, visual richness of a place, specifically, the number and kinds of entities in a physical environment. And imageability is the quality of a place that makes it really distinct, recognizable, memorable. These are all things that that are in the back minds of urban planners that we as just common citizens don't really think about. But we're really what makes a place more desirable, what ultimately brings people back to a place, are these ideas of perceptual qualities. And the ones that I've underlined are the ones that I personally focus on more, because the research community really focuses on them more. But specifically, it's it's things that how do we improve these things? It's really we really, there are ways to do it, but when we start getting into the quantitative measuring of things, it really can open up a whole new realm of how we study and look at features that are within an urban environment. So as mentioned, perceptual qualities are studied and analyzed by urban planners and designers in an effort to try and understand qualities and characteristics of built environments and make them more appealing and desirable. To understand how to manage and assess these qualities, they really have to be objectively measured. And that's the one thing that's really been missing, from the previous research, from what we're looking at here about everybody that's written works and published on this, is that it's talked about from an academic perspective, but the ability to actually physically sit there and actually measure the features to come out with something quantitative that you can actually physically measure, and something that's tangible you can measure, that's something that's really been lacking. What is the principal technology for specifically for measuring it, for measuring these features, it's Lidar. So that's perceptual qualities. Now when we're talking about the limitations for measuring streetscapes in relation to safety, and perceptual qualities, our current methods are really, what methods have we used in the past? Most of them have been audit-based methods, but they're very subjective. It might consist of a survey, sending out a bunch of university students, or just researchers going out there with a questionnaire or a checklist to check off. How big is this window? How far does it stretch? Can you see this? How many of these objects are around? We're talking about crude counts as opposed to really measuring anything, tangible. The table on the left of my screen that's cited by Purcell from 2009. What Purcell was doing was trying to basically measure perceptual qualities, but trying to do so, basically, she started introducing GIS, and compared it to these audit-based methods, and she took the audit-based methods and basically measured them and found that the correlation coefficients, as you see here, they're not very reliable. For human scale, they're not reliable at all. For complexity, maybe a little more so. But all in all, they're just not very reliable. Now, if we look at the source on the right here from Harvey Altman Hall, what you have is a streetscape, and what you have is the right-of-way, which encroaches on physical buildings. This was a LiDAR-based study. So what they're saying is if you look at inside that that periphery, and we look at the table above, we'll see that tree canopies measured, it looks like on average, and this study was done basically for a major part of New York City, and I believe a few hundred street spaces were evaluated in mass for this study. And they came up with an average that tree canopy covered about 16%, of a streetscape. The problem with that is well, one, the study was only limited to buildings and trees, which of course certainly is an integral part of what makes up a street space or an urban space. However, everything is really in 2 dimensions, which is how we often look at things in GIS, is within 2 dimensions. What exactly is happening between 0 and 5 feet, 5 feet and 10 feet, 10 feet and 15 feet, 15 feet and 20 feet? All those really depict a completely, different story than when you're just looking at something in 2 dimensions. Right? When you're looking at something in 2 dimensions, it's certainly better than just not, not having anything else to go off of. However, how much better can you do if you can find a way to really start looking at things in 3 dimensions? All right. So now I'm going to kind of morph a little more into the technology side of things. Lidar, light detection and ranging. I'm sure just about everybody on here is familiar with Lidar. It's a highly sophisticated geographic information or remote sensing technology. When collected and analyzed properly, Lidar is a much more efficient and objective method for measuring urban features than crude GIS or manual, time-consuming and subjective audit-based methods. And it really has not been adapted much in terms of fundamental transportation and urban design research. So a lot of the work that pertains to this study and a lot of the work that I've done utilizes this concept of a voxel. And as mentioned, probably most people on this call have heard about Lidar. Perhaps not as many have really heard about a voxel or specifically what a voxel is. But a voxel is basically a 3-dimensional pixel. So we take urban street spaces and we basically drive them into voxel grids. Specifically, so if you can imagine, and I'll just go back a couple slides like that. This example here of where those, the dotted lines are covering the street space, well, that's in 2D. But if you take these voxels, if I were to basically level that out and I could create a voxel grid that goes from ground level to as high as I want, let's just say 100 feet, and I can really set the dimensions of these voxels to whatever I want. Do I want each voxel to be 5 feet by 5 feet by 5 feet or 1 feet by 1 feet by 1 feet? But it really depends on the quality and the density of the LiDAR data that we're dealing with. And and the idea is that LiDAR being an aerial surveying tool, or if you're ground-based, it's being emitted from the sides. It's basically shooting anywhere from hundreds of thousands, maybe millions of points per second in point cloud. And basically that point cloud is basically going to be hitting something that will be encapsulated by one of these voxels. So let's just say that a lamp post on a street is is overhanging a few feet into the roadway and maybe 20 feet up. Surely there will be a voxel covering that. There'll probably be a handful of voxels because again, we're thinking about the entire roadway or street space or streetscape being divided up into these 3-dimensional pixels. And the LiDAR point clouds basically fill each voxel, and then a classification process occurs basically, and we can then, because we have, just like in remote sensing where we deal with with pixels and in evaluating and classifying pixels in any kind of a raster data set, well, you do the same thing with a voxel. And once the data is in there, you have something that is quantitative that can be measured. So I'll go into a little bit about the availability of LiDAR data. And the focus of what I'm talking about here is more the mobile side of things. But before we got to the mobile side of things, it was important for us to really evaluate, what data was available to the public, and the data that is available to the public is through the USGS, which is currently investing millions of dollars each year into its 3D elevation program that stands for. And currently more than half of the country is collected in LiDAR, and there's two quality levels that, well, there's a few, but the main ones that the USGS collects in is QL2 and QL1. And there's a lot of there's a whole spec sheet that talks about the differences between QL2 and QL1, but for the purposes of what we're talking about here today, what's important is that QL2 is basically 2 pulses per square meter, and a QL1 is much more dense, which is 8 pulses per square meter. And it's up to states and municipalities to write proposals, procure grants, and try to make their cases for either QL2 or QL1 data being collected. But really, the study started there because we're talking about collecting, being able to quantitatively measure features within street spaces. And the easiest way to do that, of course, is to see what is readily available. What can I just go to the USGS website and just download in order to try and evaluate what's there? And really, what we did is we did a few studies that were off of QL2 and QL1 to try and understand the limits of what we could capture in urban street spaces with those 2 different data sets. And those are actually published studies. They're published with the Academy of Sciences Transportation Research Board, and anybody who wants access to those can contact me later, and I'll surely provide them to you. But basically, the USGS lists around 30 beneficiaries of the 3DEP program. Of those, there's a few examples here. Flood risk management was being, the main one, and I put a bunch of asterisks after that one. And that was specifically because it was really, of all the different business cases, it seems apparent that was really the main driver. And the idea is that, of course, this is a federal program, and whenever there's a flood disaster, FEMA has to come in and spend billions of dollars to mitigate the situation. But I think the idea behind that was, like, if when we think about the floods in Houston or hurricanes or the Missouri River or the Mississippi River, having abnormal, cresting at such high levels, the engineers have the ability to mitigate a lot of that if they had a wide range of survey data for the areas that are potentially being affected. And the idea is well, if we spend a few $100 million on LiDAR today for these areas, it might save us $1 billion down the road, if from a FEMA disaster. And the study that was actually done about 10 years ago, they feel that for every dollar that's going into LiDAR collection, the general public is getting $6 in return. But so all these different examples are listed of what it's being used for, but specifically, what we're trying to do on our end is incorporate transportation and urban research as an additional beneficiary of this program, because that's something that really has not been discussed, is how the 3DEP program really assists transportation and urban research. So I'm actually with this slide, I am jumping ahead a little bit, because as mentioned, the work we did really started with the QL2. Once we did a study there, we moved to the QL1, and it's like, okay, We know what street features we can get with QL2. We know what street features we can get with QL1. Really, the mobile LiDAR was about filling a lot of those gaps and really enhancing the concept of utilizing the technology for the perceptual qualities of quantitatively mapping out features that pertain to the perceptual qualities of urban streetscapes. So things like street trees, you know, QL2 was sufficient for it. We found, you know, QL1 really, if it's, you know, below 5 feet, buildings, no problem with a QL2. Again, QL2 being the lesser, the much more lighter, the less dense data set. You know, walls and fences, landscape vegetation, low brush, light posts, traffic lights, power poles, traffic signs. Those all required QL1 in order to be collected. Street furniture, very limited. But you know, but if you really wanted to get some of the smaller features are really, whereas like if you had a park bench, a QL2 set might get just a few points on it. You might need, you know, the assistance of a Google Street View or something like that to see what you were looking at. You know, of course, with mobile LiDAR, it's going to paint a completely different picture. And then there's certain things that you can't really get aerially because you can only get them with a mobile LiDAR set that's emitting its pulses horizontally rather than vertically. And those are, you know, really the awnings, building windows, open air courtyards. But again, with everything, you know, light posts, traffic lights, power lines, yeah, you can get like maybe a point or two with the QL1. However, if you want the complete representation of the feature itself, you really need to utilize a mobile LiDAR mapping set. So going into the mobile project a little bit more now. So this is an area in Denver, Colorado, and we utilize basically two street spaces. One was a town center in an area called Stapleton, which really depicts what a common, typical, highly densified urban street space is. As you look at that picture, you see awnings, you see restaurant signs, you see you know, you see a stop sign there, you see lanterns, which is street furniture, you see trees, you see buildings, you see windows, you know, restaurant, courtyard restaurants, awnings. I mean, so this is basically encapsulates everything you might want to measure, you know, within an urban streetscape. And below here, this is an avenue called Mont View, and it starts in a town called Aurora, which is just to the east of Denver and ends in central Denver. And we chose that street space and divided it into 6 different areas because you know, it really, there is a lot of changes within that street space over that 4 or 5 mile segment of roadway. And we wanted to be able to really be able to understand, you know, how things change within that street space as it moves along. So this is the actual collection platform. It is a Trimble MX9. It's collecting imagery and LiDAR simultaneously. Again, highly dense. It's collecting about, you know, well, I'll get into that right here. It's collecting over 2,000 points per square meter. And we did use some ground control points. And when, you know, we did some control checks, we found that it had an RMSE of 0.6 feet or 1.83 centimeters on the horizontal and a bit more on the vertical. So as you can see, you know, very dense and also very accurate. You know, and here's another thing, as mentioned earlier, a user that is studying an environment with voxels and LiDAR has the ability to actually set their voxel parameters. So here, the voxels are actually, I say reduced. The reason I say that was because for the QL2 and QL1 studies, they were much bigger. I believe they were 5 foot by 5 foot by 5 foot voxels. But since we're dealing with, but as mentioned earlier, we're talking either 2 points per square meters or 8 points per square meters. Here we're talking 2,000 points per square meters. So we reduced it heavily to 1 foot by 1 foot by 1 foot. And we also use a lot of tools in Esri to, to automate the actual processing. Well, the actual LiDAR data was not processed, but once we actually got derivative products from the LiDAR data, a lot of that data was really derived into different Esri model builder processes and some automated functions. Because here's the key thing here is the last 2 words of this slide, which is descriptive statistics. Ultimately, everything that we're doing is to try and get linear descriptive statistics, I should say tabular and linear descriptive statistics of what exactly is in the urban environment. And in order to get that, then we're just kind of using some back-end GIS work. So a few limitations to the work we did. So we're going out there, we're collecting a whole bunch of LiDAR data. Of course, when you collect it initially, it's it's raw LiDAR, it's not processed. Everybody's looking for that one button that you can push that's gonna, basically classify everything into anything that you want. So again, just going back a few slides here, what is that one button that I can push that's gonna just say, boom, just put everything into these different categories of features and point cloud, and boom, we're done. That hasn't quite happened yet. There are a lot of researchers that are really looking into different methods. And of course, now that within the past few years that AI has really, hit the scene, I suspect that that over time, the automated methods are going to improve. But right now, if something is collecting something and it's like 80 or 90% correct, and you're going to get all these false positives and you're going to get all these false negatives, it still has to be evaluated manually. So there are some parts you can do in an automated way, trees, buildings, for example. But there still is quite a manual haul to classifying a lot of this data. And there are firms in lower wage places that can crank out a lot very quickly. But I would expect that within the next, I'd say even 5 years or so, that the industry is going to make significant leaps in the ability to classify LiDAR point cloud in an automated fashion. And another thing to address is occluded data. And the reason I address that is because it came up by various researchers that really inquired about it. And it is true that an area must be clear of hazards like parked cars and etc. When we did our collection in the area that when we did our collection in this area, right now you see all these parked cars down the street. Well, when we collected, it was actually, during COVID a couple of years ago, and there weren't really that many cars, and it was early in the morning. So we didn't really have any issues of cars not being parked on the street. But, if it is a city effort, they might have to, find ways to prohibit cars from being parked when this work is being done, because anything that is, say, at ground level, like the street furniture or the tree trunks, if a LiDAR sensor is going down that street and trying to collect that, a lot of that's going to get missed. So, that is something that has to be kept in mind. Another issue is if you're collecting from the side the way that you are you really collecting everything? And the answer is yes, for the most part, and that's based on comparative published research that shows that occlusion is really not an issue. So now we're getting into a little bit of the of some of the collection results. I think a big thing to look at here is that street space on the left-hand side there, that intersection. Yes, you are getting a lot of representative data from the USGS QL1, but again, it's kind of what kind of a picture are you really looking to get? Whereas the poles and the wires and things, and the overhanging lights, they're much less represented in a QL1 data set than with a mobile data set. And you can see here that everything again, it really depends on what your ultimate goal and what you're trying to get at and evaluate. But clearly there's an immense difference when looking at a data set that is collected in QL1 versus mobile LiDAR. Looking on the right hand side there, it's that, for example, I pick out that no parking sign because it's really hard for an automated system to really look at that entire pole and to pull that sign out right now. It's an example of why it's important to do a manual process is still relevant, and why we really haven't gotten to the point where where automated methods can really take over. And it's because right now there's really nothing out there that would really be able to pull out a feature like that. And also, if there's a hydrant in a bush on that bottom right figure, in a QL1 data set, all you're going to see maybe is just a couple of points there. You would need to have a street view next to something like this to really to understand what's there. This really shows just how how really in line the mobile is to the mobile LiDAR is to the actual image. I mean, what's interesting here is you have two garbage bins here. You see them right there. The street sign. The way that bench is painted. It's really the point cloud from a mobile collection is really it's really depictive of the actual environment out there. This is from our study area in the town center. Everything is broken out into its different individual features. This image right here is really an attempt to really, I mentioned earlier that that 1 cubic foot voxels were used to really cover the street space. It's really hard to get a good image to encapsulate what that looks like, but I mean, this is one of the closest things that I could come up with just kind of throwing those voxels in there and just trying to angle the image in the LiDAR processing software a certain way. But the idea is that these are all cubes, and the LiDAR features fall within these cubes, and therefore are classified. So I mentioned that again, going into those perceptual qualities of what makes an urban environment is the ability to to really measure things that nobody really measured before. And it is a concern, how much building face, how much window coverage, for example, is in any given street space. And this is a way that we evaluate it. It's for this we used a software, I believe Bentley owns it now. It's called Orbit 3D, and basically with the imagery tied to the LiDAR, we were drawing 3D shapes of the actual windowsills themselves. And then again, with the help of Esri Model Builder, we basically ran a process of creating a triangular irregular network of each and every feature in order to be able to measure what the actual surface is. Now, why did we do that? Because again, if I take these shapefile like this and I throw it into Arc Pro, all it's going to show me is a line, because it doesn't really work in 3D. I mean, well, I guess with Arc Pro now there are some 3D settings out there, and a lot of this work was done 2 years ago, before there was that there was much less of a move from ArcMap to Arc Pro. But for those of us that are still in ArcMap, so to say, you're going to throw that in there. It's just going to be like, viewed as a line, but it's really a 3D feature. However, if you convert each one into a raster and just take a tin of it, what the tin will do is it will take basically where the feature is in space and how long it is, so how long and how wide it is, and be able to calculate an area of it, basically a surface area, which is ultimately what we're looking for when we want to quantify something. So, I showed you guys in the previous 4 or 5 slides, a bunch of very fancy pictures of LiDAR features being collected. Now the question is why does all this really matter? It's that's a question we often ask, and a lot of what we do is you can sell somebody a technology that's going to be able to fly through a canyon and see everything, and that totally is very cool and all, but what's the practical application? Why does that, what you're doing actually matter? And as I mentioned earlier, it matters because we're just trying to get everything into descriptive statistics. So these are descriptive statistics for the town center area. We broke that area into 6 different areas, and specifically, everything we're looking at here are either in units of square feet or cubic feet. So we're calculating the different tree volumes, and it's interesting to note here that as far as the points go between areas 5 and 6, which are very similar areas, there was a much different tree volume, but we actually can calculate the square footage of how much street sign area there are, hanging street signs within the street space versus counts. But also over here we have the hanging signs, so like signs that are calling out restaurants or other stores. How much actual physical area coverage are there, and if we really want to, you can just calculate that against the area of the streetscape, which is down in here, and you can actually get a figure of a percentage of coverage. And it's the same thing with street furniture and how much is covered there. As we see here, area 2 has maybe 4 times as much as areas 5 and 6, yet they're similar areas. And then of course there's the crude count as well. So you have the crude count, but taking it to that next step, you actually have the actual area coverage of how much is out there. And if I move down to this second row down here, I talked earlier about window area and how much percentage of a specific street space is covered in how much of the side of the area is actually covered in windows, and that can all be quantitatively derived, as well as overhanging awnings. So what we're looking at here is basically a whole realm of descriptive statistics, and it certainly doesn't end here. It can go as far as any urban or transportation researcher wants to take it, in terms of ways that they can quantitatively evaluate what's out there and then utilize those statistics to try and enhance and improve their areas, and ultimately make them more desirable, make them just better cities, better environments for their children to grow up in, or better environments for people who just want to get out and walk around and just be in a peaceful, pleasant area. Oops. Again, related to these perceptual qualities, so I talked about them a little earlier, and these are just some examples. The street trees, they help capture enclosure. Lights, lamps, trees, furniture, human scale and complexity, window areas and proportion, factors of measuring human scale and transparency. Hanging signs and fenced courtyard restaurants are measured for imageability. Moving into that, the different example that I showed you, which was that 5-mile length of street. So, the last slides I showed you, were pertaining to the town center. This pertains to the I'll just jump back there real quick. So this Mount View Avenue right here. So the next round of statistics are going to go into that. And what we're looking at here is what goes beyond the QL2 and the QL1 in terms of being able to map out what is visible. So I'll try and explain this real briefly. I know that in the interest of time, I'll try and keep it a little quaint, but but we have basically SS is the street signs, TS traffic signals, SF is street furnitures, and with these different numbers here are basically the voxel zone from the ground going up. So we had 1 foot by 1 foot by 1 foot voxels, and basically anything that is a 1 is at 0 to 1 feet, a 2 is 1 to 2 feet above the ground, 3 is at 2 to 3 feet above the ground, so on and so forth until you get to street signs here, which is 23 to 24 feet above the ground. So we see here that when we start getting to 6 feet above the ground to about 12 feet above the ground, that is where all the street sign coverage, again, is an area. These are not crude counts. These are actual square footage areas, or I should say cubic feet. Sorry, they're areas of cubic feet. I say cubic feet because they're 1 foot voxels and 1 foot by 1 foot by 1 foot voxels. So each one of these units represents a single cubic foot voxel as its individual unit. So you actually see here where the street sign density is, but within the different areas you can start to evaluate what areas have these signs at different levels, and when you start weighing that against information such as crash data or crashes against pedestrians with bicycles or other incidents, you can start to utilize that to determine, well, hey, maybe it is a better or safer practice to move signs a little lower, signs a little higher, and so on and so forth. And the same statistics are available for TS, which is the traffic signals, and SF, which is the street furniture. And of course, as mentioned earlier, street furniture is certainly aside from the safety concepts, which as I mentioned earlier, there's a lot of research out there that yes, street trees, but again, that other objects within a driver's periphery actually heightens senses and heightens awareness. But now you can actually quantify that to say that that the more street furniture features we have in in an urban street space, the safer it is actually for drivers and thus for everybody that interacts with it. So, in conclusion, the study offers new and objective methods to quantify streetscape features in an environment that they're considered walkable, and they can really supplement or even replace the highly subjective methods used by audit-based 2D GIS analytical methods. The methods for objectively measuring street features can help redefine the role street features are attributed to specifically to road safety, and of course what makes a place more desirable. And and of course, as we all know, with the growing use and the growing the technological improvements of GIS remote sensing, specifically LiDAR technology, I would really think that in the future we're going to be seeing a lot of more of this work specifically for these related purposes. So for anybody interested in just kind of reading more about this, this study about high density LiDAR for measuring urban streetscape features, it was published last year in the Urban Design International journal. I have a link you can just find me on LinkedIn, and within my LinkedIn page, you can link directly to the publication. It is available to the public.